Okay. Voilà. Okay, so I will speak about what robot can learn, so how robot can learn to control haptic interaction as humans do. So we will first see how human learn, how they learn new dynamics, how we could model that, and how now we can use this for robot application. And so it is interesting. So this was about 10 years ago, then 5 years ago, and now the robot. And what? Okay. What is interesting is that when we did this motor control experiment, we had no ideas that it could be one day useful for robots, and we didn't care about that. And it came gradually. We noticed that yes, it can be used for robots, and then it's doing something that was not in robotics before. Okay, so first. Quickly, what we do with my group, so we do motor control experiment and computational modeling, and using this knowledge about human motor control, we develop applications like this brain control wheelchair, training for microsurgery, and also robot-assisted rehabilitation after stroke. So these are some of the people I continue to work with. So I was first in Switzerland for the studies. After I was for the postdoc in Canada and Japan and a bit in US. And after 5 years in Singapore, and I'm now in the UK and working also with people in Europe. So these are some of the people. So many of these people have contributed to some of what I will show today. So what is the problem of a robot? So the problem of a robot is that the robot has a body, and he has to move with actuators. This robot has very limited knowledge about the body, at least at the beginning, and doesn't know the environment a priori, because we never know the environment perfectly, and also. It's costly to recognize the environment a priori. So this robot has to perform new tasks and in changing conditions. So even if you know an environment, it's not sufficient because you will come to another task, to another interaction, and to another environment. So you have to start all again. So the situation seems to be difficult. However, this robot has a lot of sensors and can from the movement it's doing, it can recognize the effect of the movement on the environment, and then from that maybe try to understand what to do and how to control the movement better. And so the way to go is to develop motor learning to improve task performance in interaction with the environment. And for robots, you have to work with humans because robots are done finally for us in principle, for us humans. So the way is to use this information from the sensors, look at the experience I get doing action, and then improve performance by learning gradually. And of course, it's exactly the same that humans have to do. So if you consider humans, so you have to learn during infancy, you have to learn also, so when your senses are changing, when your capabilities are changing, for example, when you get older, your capabilities go down, and then you will have to adapt to that. And also we have to learn new tasks every day. So the situation between the human and the robot have a lot of similarities. So based on that, so we will first look motor learning in human and robots, then we will go to learning what is happening in unstable dynamics and with noise, And then we will see how these learning strategies can transfer to robotic strategies. And finally, we'll speak about generalization. So first of all, why do humans need to learn? It's because, in particular, because we have a very long delay with sensor input. So if you have a robot, nowadays you have typically a delay in the feedback loop of 1 millisecond. So from that you can control, and you don't have to control much in advance. However, so for human as well as for robot, when you come to visual processing, for example, then you get delays of typically 100 milliseconds or more, depending on the scene, what you want to recognize in the scene. So you have a problem with the delay that can bring, of course, instability if you control with the sensors. And so if you want to perform skill action in particular, so as you need to manipulate object, then you need to compensate for the environmental forces and for the instability with the environment. So this is, so you know, most of you know that or have something like that in the lab. Sorry, I don't have it yet. So this is a big haptic interface you use, so you can, in this case, you perform planar movement. You have interfaces to perform also 3D or 6D movement, but these planar movements are still good because it's simple, you can measure very well, you can have a stiff interaction or a compliant interaction, and you have a nonlinear system, you have coupling, you have a redundant system of muscles, so you can understand already a lot of things by observing this planar movement. So this is a typical, so it's a bad video, bad quality, but this is a typical experiment where you do a movement from the start to the end, and so you have this robot, you measure the force here. You have the big motors that can also sense the position and impose force field. So here it's without force field, so you have been performing in a straight line approximately. And yeah, so here it's again a free movement. If you repeat, so here you have seen that it was deviated to the right because you have a force field, and you do the movement again, and here you have seen that you have been deviated to the other direction. So this is this typical experiment. I'm a bit repeating what Joe has presented a few days ago, but I want to look closer to the learning. So this is free movement, so null field, so free movement. Now, when you put a force field, for example, this velocity-dependent force field, then you get this shift to the left, and gradually you converge to the straight line. And this is after learning, and you have the after effects that are catch trial that show what the brain has memorized. So you expect to have to push against the wall, and there is no wall, then you fall to the other side. And okay, so when we analyze a bit closer, we see that you have a monotonic conversions to the straight line. So you have the first trial, the second trial, the third trial, the fourth trial. So roughly it's converging to the straight line trajectories. And when you analyze the error, so this is left, this is right, then you see again that you gradually converge to zero error, and after you oscillate a bit to the right or a bit to the left. Okay? And the after effects are going to the right, as you see here. And you see that you change the force. So this is the force after learning in this VF. So you have changed the force in the X direction to compensate for the force field. So, so this is what we can model. So we have, okay, so what do we have? we have the task. So the task is to move the arm and to interact with the environment, okay? And of course, we do this with the muscle. The muscle, what are the components? So first we have the motor command. The motor command is going to the muscle, and then we get a force from the muscle. We have also the intrinsic properties of the muscle, the viscoelasticity of the muscle, that makes like a feedback. It's not a feedback. It's just mechanical properties, but it's acting like a feedback. If you disturb, it tends to come back to the undisturbed position. And you have the neural feedback. This is really feedback, and then you have this feed forward. That what you learn trial after trial. That is trained by the neural the feedback error. And so this is a model that is relatively old. So it was proposed in '87 or a bit before. And so what does this model say? So how does it work really? So if we look a bit closer, so at the beginning you have no feed forward. You learn, for example, from zero, or you learn from another feed forward. And then you have feedback, right? And with this feedback, you can already do the task more or less, right? So if you look here, even the first time, you are not completely wrong. You do about the movement. So it means that the feedback is providing something that is close to the task dynamic. So you can use this knowledge of the task dynamic and put this as feed forward in the next trial. You put some of this as feed forward in the next trial, and then what you see is that the feedback then is decreasing. And you do again, so this feedback is again something that is missing in your model of the task dynamics. So you incorporate some of it in your feed forward, and then the feed forward is growing gradually to the reproducible dynamics, while the feedback is decreasing to almost zero to the irreproducible dynamics. Okay? So it's a very, very, very simple principle. So how this works, so you have that the torque at the joint is equal to the feed forward plus the feedback, and you start with feed forward 0, and you incorporate, so you learn feed forward trial after trial, so K is the trial index, and so the feed forward is increased by part of the feedback at every trial. And in this way, you can learn nonlinear dynamics along one repeated trajectory. And for robots, this is something that is very useful because, as you know, in industry, still most robots repeat the same trajectory, the same task. So in this way, you can learn nonlinear control. You can also learn interaction forces, and it's working pretty well. So this is an experiment with a robot long time ago. So you have this robot that had to be trained so that we can control an inverse pendulum. And so you see that the error is dropping along the time. So we have a periodic trajectory. So you do the trajectory, and you do it again, and you do it again, and you do it again. So you have the time here. You see that the error is dropping. And after learning, you see that the feedback here has dropped to quasi zero, to very, very little. And the feed forward is almost equal to the total torque. And this is working so well that you can get a very good model of the plant dynamics. And actually, we have tried, for example, to cut the feedback, and the robot was performing well for about 1 minute without any feedback. Okay, so that's something that is working very well in robots. And so what is that doing in human? So as a model of human learning in a new force field, you see that, so this is this measurement of human movement. So this is first, second, third trial, and so on. And you have a similar adaptation in the simulation. So this is an algorithm that gives good prediction of force and trajectory. So to show again, so if you generalize this to not only one movement but several movements, then you get adaptive controls that was developed in the same time at this Cavator's model. Actually, it was developed by the end of the 80s. You have many people associated to that. So, for example, Wen, Craig, Slotin, Horowitz, Cavator also, actually. They all pretend to be the first. And they were all together about, and it doesn't matter, but what does matter is that this is a very efficient algorithm. So this is how so you have these big robots with 6 degrees of freedom. This is a parallel robot with 3 wheels, and it's moving. So what it's doing now, it's making the gymnastic, it's making the training, and with a training of less than 1 minute, you can learn the dynamics so that you can divide the tracking error by 10 or more. So this is now incorporated, this algorithm, in several commercial robots. So to summarize this part, so human and robots have to learn because they cannot rely on a model. In particular, when you have new dynamics, when you interact with dynamics, you cannot know it in advance. So it's better to learn than to model. And so when repeating movement in a novel environment, humans gradually compensate for the interaction force. This is for a stable environment, stable interaction. And this is well modeled by iterative learning. That's what we have seen before, these algorithms that learn trial after trial. And this iterative learning is a very efficient control algorithm that can be used, that is used with robots. Now we continue to the second part, so we will speak about how humans learn in unstable dynamics and with the noise. So we have seen many stiffness ellipses all about the week, so I defined it quickly so that we all know exactly what it is. So what you want is to visualize impedance. So impedance, if you linearize the system, it can be seen, it can be viewed as composed of stiffness, damping, and inertia, right? Now, you want to visualize these 3 components, so you use these ellipses. So what you do is, for example, for the stiffness ellipse, you consider a perturbation in one direction, and you compute the force associated to that, the restoring force. If you shift like that, then it tends to come back because of the spring force. Now, you do in another direction, and another direction, and another direction, and in all directions, and you plot these ellipses that illustrate the strength of the elastic response. And in this case, for example, you have a larger response in the long axis than in the short axis of the ellipse. And now, so you know, so we have seen some ellipses. So you have the inertia here, you have the viscosity and the stiffness. So what you see is that the inertia cannot be changed, actually, as it can be changed only by changing the posture, as Neville Hogan mentioned in his presentation. But at a fixed posture, you cannot change the impedance. Now, both the viscosity and the stiffness change as a function of the applied force. So when you apply the force, so increasing force in that direction to the x or increasing force to the y in that direction, then you see that the ellipses maintain exactly the same shape, but just increase in size. So you have roughly a linear increase of stiffness with the force, and you have also an increase of damping that is not linear, that is growing a bit less than linear, a bit like the square roots. And so this both stiffness and damping increase with the force or with the muscle activation. Okay? And of course, this is very important for stability, for movement, because stability is provided by the kind of PD controller provided by muscle, viscoelasticity, and reflexes. And so this stiffness and viscosity provide generally stability during movement. Now, one thing to mention is this, so this may surprise you. So humans cannot control impedance voluntarily. So what I mean by that is that, so if you want to apply a force in one direction, you can do this very well. Now, if you want to stiffen exactly in one direction, it's much more difficult. And in fact, people, so the group of Hogan and other group tried hard to demonstrate impedance control in human by asking human or by forcing human to stiffen in one direction, but it is not so easy. You cannot think, okay, I want my stiffness ellipse to be oriented that way and do it. You cannot do that. So in fact, to do that, however, I mean, we know that we can deal with instability. So when we have a tool, it is unstable. If I press more here, it's going to the right. If I press here, it's going to the left. And so this is an unstable situation. And of course, to fight against this instability, I'm certainly using the impedance of my arm. So now we wanted to understand how that works, how human can learn to do that. And this stability is quite important for the brain also because, so, okay, when you have a stable situation, a stable interaction like opening a door with friction, you open the door with friction, the first time you may be surprised, but the second time you will no longer be surprised. You know exactly the force you have to produce. In an unstable situation, it's very different. So if you go to the right one time, it doesn't mean that by pushing more to the left, it will work the second time. In fact, you will fall to the left. So the brain needs stability because if you want to plan anything, then you have to have stability so that you can know if I am doing that, I will get this effect. So the stability is especially difficult in human because we have a lot of noise. So, for example, if you press again a force sensor, you have to maintain visually this level with your finger. Then you calculate the standard deviation of the force. Then you have noise, and the standard deviation of this noise is increasing with the force. And this motor noise is so important that you have this absolutely not negligible deviation in movement. So if you want to do the same movement, you never do exactly the same movement. So this is this variability that you have trial after trial. And so so it is strange that we are able to deal with unstable situation despite this very important noise. So to understand that, we designed this experiment that people have talked about. So you have to go from the start to the target. You have this destabilization force field so that you go to the left or to the right if you are a bit to the left and to the right. And this is, so these are trials so in three directions as David has mentioned yesterday. So if you have instability in this direction, so laterally you have these trajectories first. If you have at 45 degrees, you have this deviation like that, and here you see the effect of this. However, after about 100 trials, then in all conditions, you get you get movements that are similar to free movements. And again, this is quite important for the brain because when you have movements like in the free condition, then your brain can plan exactly like in the free condition. Yeah, so this is probably due to a change of impedance. We knew that, and that's why we measured that, and David has again shown this. So you see that in all subjects, you have an increase of impedance corresponding to the force that is exerted so that you compensate for the instability. And in fact, if we look at, so this is the experiment that David has done, and you have the strength of the force field from 200 Newton meter to 500 Newton meter. And so what we wanted to see is, so when I did the first experiment, I thought, okay, I'm increasing impedance only when I have to, when I cannot succeed with a task. But maybe if I can succeed, so for example, with 200 Newton meter, you can still succeed and get the target, then perhaps I don't need to increase impedance, so I will not do it. However, what we found is that you increase impedance in all cases. You increase impedance, and you increase impedance in a way that the net stiffness is about always the same. So when you subtract the impedance you have learned, you subtract from the impedance you have learned the impedance from the environment, the instability, then you get always the same net impedance, the same stability margin. And that's something that is nice because, so it means, what does it mean? The same stability margin, it means the same deviation. And it means also that the brain has always the same condition independent on the environment after learning. So if you have the same movement after learning, independent on the environment, then for the higher level of cognition, for the higher level of planning, then you can use always the same plan, independent on this low level. Okay, we were quite surprised of this result, and that's why we started to develop a computational model to understand how that works. And so we started with relatively complex strategies, complex algorithms, reinforcement learning, etc. And we came to something much more simple gradually. And the point is that, so when you observe the error in a trial and you observe the change of motor commands, of muscle activations that you measure by EMG, by surface EMG, when you plot the change of EMG as a function of the error in a previous trial, then you find this V-shaped function. So this is for one muscle, and so this is for an agonist muscle and for an antagonist muscle. So you take muscle in pairs, and so that you can control force and impedance and the joint separately. And then you see that you have both V-shape and symmetric V-shape function. So how does it work? So if you have this V-shape function, so this change of motor commands as a function of the error in previous trial, so what do you find? So what you find is, yeah, of course, the change of torque at the joint will be this flexor minus the extensor. So, for example, it makes that if you deviate to the right in one trial, then the next time you will push more to the left so as to compensate this deviation to the right. What is interesting and what is new is that because when you change the activation, when you increase the activation, you in fact increase the impedance. Then, so when you increase in the flexor and the extensor, you increase the impedance of that much. And so what happens is that you do a movement to the right, and then you increase you increase the force, especially with this muscle, but you increase also the impedance. And after you go to the left, and you increase the force to this muscle, but also the impedance. And you gradually build up, so you build up co-contraction by increasing left and right, and by increasing the impedance in both muscles. And after sometimes, because you have increased activations and you have a better PD control, you have better stabilization, and then you have less error. And when you have less error, you have a decrease of activation. So you have a balance between minimization of error to improve performance and minimization of metabolic cost. And by this concurrent minimization, you get the progression of the learning. So we have tested this in a simulation. What we had is, we had a model with 2 muscles at the shoulders, 2 muscles at the elbow, and 2 double joint muscles like the biceps and the triceps long hand. And we could compare because we had measurement of EMG as well. And so this is a simulation, and you see that both in a stable interaction where you have monotonic change of trajectory and increase of force, or in this unstable interaction where you have divergent movement first and after a stable convergent movement, then you reproduce the pattern of the learning. And when you look at the stiffness ellipse, so this is in NF conditions, so before learning, this is in VF, so in this stable interaction where you change the impedance because you change the force. When you change the force, it's changing the impedance. So this is not impedance control, it's just a byproduct of mechanics. And then in this unstable interaction, you have an increase along the direction of instability, and this is similar to what you find in the experiment. What is, in my opinion, more interesting is that you are able to predict the change of muscle tension trial after trial. So you have, for this unstable interaction or for this stable interaction, so you have along the trial for the shoulder muscle, the biarticular muscle, and the elbow muscle, the change of muscle tension or muscle activity. And you see that, so for example, in these stable interactions, then you have a large increase first and a gradual decrease, and you come to a level that is different from the NF, right? Because you learn a force, especially in this extensor muscle. And for a stable interaction, an unstable interaction without force, then you just co-contract at the beginning, and after it's slowly relaxing, so that you can stabilize with minimal co-contraction. And it is interesting that we can really do trial after trial or time after time, because in most scheme of optimal control, for example, you have before and after, and often you have to rely on a model. Here it is model-free, and you have the whole adaptation along the movement, and it is important because if you learn trial after trial or time after time, you will get, for example, in local minima, you will have bifurcation, all this kind of phenomena from local optimization that you would not get from a global optimization with optimal control. Some prediction, because in fact we had fitted to free movement. We had a few parameters. We had fitted to free movement and to the beginning of evolution in one force field. And after we didn't change any parameter, and we just made click in different conditions and just saw what is happening. So, for example, this experiment that was done by David in Japan. And we were doing simulation in Singapore, so we had no connection, and we connected after. And interestingly, you have a very good match. So if you compare the orientation of the ellipse, you see that so it's very similar in experiment and in simulation, and the same for the shape, except for this 80 degrees here. And what is interesting also, so you have again this prediction of muscle activation, the evolution of muscle activation, and we don't have data yet to look at that, so this is a prediction. What is interesting is, of course, that you have 6 muscles, so you have a redundant system, and the algorithm is able to solve the redundancy by itself, without any inverse, pseudo-inverse or whatever. Okay, now another use of this model, another prediction is what is happening when we change noise. Because, so for example, when you get older, then you become less accurate. You have more variability, okay? Or if you have a tremor, so pathological tremor, then suddenly you have more variability. So we use a model to predict what we think should happen from the point of view of impedance. Yeah.
Before you move on, I guess the 2 slides ago, the orientation of the stiffness ellipse in the null field seemed also very different. Can you comment on why that was in your experiment?
In fact, the measurement of the ellipse is relatively sensitive. So it's like that it's a bit different, and do not forget that it's in movement, right? It's in movement, so it may be also that from one subject you are in the middle of the movement, and for another subject you are not exactly in the middle of the movement, and so on. And because the force that you produce to perform the movement will influence the shape, it may change. But it doesn't affect our result, as we look always at the difference between after learning and before learning.
But what you said about during movement and when in the movement you measure would affect how much variability there is in your experiment. That shows up as a large variability. But your simulation was outside, it appeared outside of the entire range of.
Yeah. So
like a simulation had a consistent rotated ellipse.
So we measure in the middle of the movement, but the middle of the movement does vary from person to person. No? I mean, it depends how long you do the movement, and the orientation, actually the shape of the ellipse is relatively sensitive to many factors. But what counts is the difference, in our case, what counts is really the difference between after learning and before learning, and this is very clear. Okay, so what we find for the effect of the noise is when you increase the noise, so you have less noise and more noise, then it is increasing the stiffness ellipse, and especially so it is. So you have the same shape, but it's just increasing the size. And of course, you should have an increase of impedance that is larger in the DF, so in the unstable conditions and in the stable condition. And of course, it means also that the impedance grows stronger than the noise, right? Otherwise, you would not be able to stabilize your movement. Okay, so the summary for this part is that, okay, so the interaction with the environment can create instability. In fact, it's creating, most of the time you are using tools. And this is amplifying the already large motor variability that you have in movement. Now, the CNS, the central nervous system, automatically learns to coordinate muscle in order to stabilize unstable movement and to compensate for the force. It really is automatic in the sense that even myself, if I do the experiment now, I cannot I cannot be different from naive subjects. It's not something that you think about. It's totally unconscious. For example, the first time, if you go to the right, the second time, in most cases, you will go to the left. Even if I know and I want to fight against that, I cannot. So, with this learning, the CNS producing the same stability margin independent on the environment. And again, I think this is an important aspect because the brain may use that to make planning and higher cognitive function. And this learning can be described with a simple algorithm, so this V-shaped function, change of activity, and it's correctly predicting the whole evolution of muscle activation during the training. So we can so predict the muscle activation, the joint forces, and as well as the endpoint force. And also the impedance in the muscle, in the joint, and at the endpoint. Any question? You can cut myself whenever you want.